What is Fundamental Theorem of Arithmetic? Let's try to learn that. So, as per this theorem, every composite number can be expressed or factorized as product of primes. So, let's stop here. So, there are two things that is being said in this theorem. First is every composite number. So, what is composite number? So any number that has more than two factors are composite numbers. For example, 6. The number of factors of 6 are more than 2. 1, 2, 3 and 6. So this is a composite number. So every composite number can be factorized as product of primes. So basically it says that you pick any composite number on this earth and you can factorize that. You can write it as product of prime numbers. So that's the first thing that this theorem is trying to say. And secondly, this factorization is unique. Whatever that number is, and when you would prime factorize that factorization would be unique, irrespective of the way that you do it, apart from the order in which prime factors occur. Let's understand this through a quick example. Let's say that we have a number 24. And we are trying to prime factorize that. So let's do prime factorization using factor tree diagram. So 24, we can write it as 2 times 12, right? 2 12s are 24. Now 12 is not a prime number, so we have to continue this. We can stop at 2 because 2 is a prime number, but 12, we again need to factorize it further. So 12, we can write this as again as 3 times 4, 3 4s are 12, 3 is a prime number, so fine, but 4 is not a prime number, so we have to continue. So 4, we can write this as 2 times 2. Now we got all prime numbers, so we can stop here because we cannot further prime factorize this. This is itself a prime number. So 24, we can basically write 24 as 2 times 12, 2 times 12, but 12 was further factorized as 3 times 4, 3 times 4, and this 4 was further factorized into 2 times 2, 2 times 2. So basically what we are doing, we are picking all the numbers that are at the end of any of the branches of this topic tree. For example, you can see here we picked 2, 2, we picked 3, we picked 3, we have one more 2, we have one more 2. So we have 2 2s here as well. So this is the prime factorization of 24. Now, why is this unique? Isn't there any other possible prime factorization? Let's actually try to do this. Let's try to prime factorize 24 in other possible way. And let's see whether we get to the same conclusion or do we get some other prime factorized form. So let's start with prime factorizing 24 again. This time we can write 24 as 8 3s are 24. Now 3 is a prime number, so it's fine, but 8 is not prime, so we have to continue. So 8, we can again write this as 2 times 4. 2 is prime number, but 4 is not prime, so we would again continue. So 4, we can split this as 2 times 2. Now we have only prime numbers available, so we can stop the prime factorization here. So as per the second tree here, as per the second factor tree, we can write the prime factorization of 24 as 8 times 3, 8 times 3, but this 8, we wrote it as 2 times 4. So this 8 was written 2 times 4, and this 4 was replaced with 2 times 2. So let me actually write that neatly. So 4, we would replace 4 with 2 times 2, and this 3 would come here as it is, times 3. So how many number of 2's do we have in the first prime factorized form? So we have 1, 2 and 3. We have 3 2's, that is 2 to the power 3 times 1 3. So 2 to the power 3 times 3. And in the second way, how many 2's do we have here? So again we have 3 2's. So we can write this as 2 to the power 3 times 3 times 3. So irrespective of the way you prime factorize any number, the final prime factorization remains the same. And one more thing, that apart from the order in which prime factors occur. So prime factors can occur in any possible order. Like we can see here. Here first we have 2, then 3, followed by 2 2s. Here we have 3 2s followed by 3. So irrespective of what order they occur in, the final prime factorized form, the number of prime factors, number of unique prime factors would always be the same. And that is what this theorem is trying to convey to us.